Hi, I am Sricharan. This is Digital Signal Processing Lab 4. Today we are going to find the magnitude spectrum of a signal sampled at 25 Hz using DFT algorithm. In this, we'll use matrix representation of DFT to compute DFT coefficients for a given signal with a duration of 3 seconds. Then compute period of a signal using autocorrelation method, and we'll compare both the pitch period values. As you know, autocorrelation function. In the previous video, I told you that R of m is equals to 1 by R of 0 into sigma n equals to 0 to n minus m minus 1 x of n into x of n plus m, where m is from 0 to n minus 1. ACF reveals how the correlation between any two values of a signal changes as their separation changes. DFT, that frequency samples that are obtained by evaluating the Fourier transform x of omega at a set of n equally spaced discrete frequencies is called the discrete Fourier transform of x of n. This is the equation x of k is equals to sigma n equals to 0 to n minus 1 x of n into e power minus j 2 pi n k by n, where k is from 0 to n minus 1. And then we'll assign this e power minus j 2 pi n k by n to wn power kn, where wn is equals to e power minus j 2 pi by n, from k is from 0 to n minus 1. Now I'll explain the code, DFT code. Uh, the given signal has 75 samples. Since it is sampled at 25 Hz and it is of 3 seconds duration, so my 25 into 3 is 75. There are 75 samples, n equals to 75, and uh, then we are going to find the we know that w is complex. As said in the equation, wn is complex, so we'll find the imaginary part and real part separately, and we'll multiply that real part and imaginary part with x of n, and then we'll find the magnitude. This is the procedure. In this for loop, we are going to find the imaginary and real parts separately of w of n. This is real part and this is imaginary part. In this for loop, we'll get the wn matrix. Then we are we are finding moving average of given signal. X of I is the moving average filter output, and then we are finding the multiplication. We are multiplying x of n with real part of w and imaginary part of w, and then we are finding the magnitude, that is square root of r sum into r sum plus I sum into I sum. That is, if you want to find the magnitude of some complex number, that is x plus ij, then x plus iy, then we will find the magnitude as follows. So under root of x square plus y square, that is the same procedure is followed here. And then once we get the x of k values, we'll find the dominant frequency index. That is, if there are lot of frequencies that dominant frequency means for which frequency the magnitude of spectrum is maximum, and we'll find the index of that frequency and we'll store it in I, and then we'll find the BPM. I already uploaded the code. Now we'll find the, I'll show you the plot. There are two dominant frequencies, there are two maximum amplitudes. And I got the uh, BPM as 60. I'll show you 1 second. it will upload, and I will explain. Until then I will explain the second code. This is the same. We are going to find the same pitch period, and the procedure is different, that is by using autocorrelation. And the same signal with 75 samples is given here, and we are going to divide the signal into 4 blocks. And then we are going to find the moving average filter output, and then we are going to find the mean of the signal. These all codes are explained in the previous video. And we are going to find the moving autocorrelation of given signal by removing the mean. And then as we know that zero r of 0, where r is the autocorrelation function, r of 0 is the power of signal. So we'll, to normalize the signal, we have to divide the our autocorrelation values by power. So we are going to divide the autocorrelation values with power, and then we are finding the first zero crossing. That is, after first maximum we are going to find the first zero crossing, and then uh, we'll start the signal from first zero crossing to the end, and then we'll find the we got the signal from first zero crossing to the end, that is z of k, and we will find the first maximum of z of k, z of I, and then we'll get that index, and then we'll store it in t. And this is the k. Since this is in this first maximum, the signal is taken from first zero crossing, we have to add the index of first zero crossing. So we are adding k value to t, and then we are finding the bpm. And I'll show the output of this code. 60. As I said, this is 60 bpm. We got the 60 bpm in using DFT. And then now we will see what we'll get in autocorrelation method. That is 93. We are getting 93 as value. 93 as bpm by using autocorrelation. There is some error because we are using autocorrelation value. There will be a difference. And then we'll use the same method to find the bpm using MATLAB. And here we are going to find the same. We are going to do the same procedure. We are going to assign the samples to a variable, and we are going to find the length, that is n is 75 and fs is 25 hertz, where moving average filter length is 8, and k is n minus m, that is to find the moving average filter output. And now we are going to find the moving average. First we are passing the x through moving average filter, and y is moving average filter output. Then we are going to find the DFT matrix. Here we can use directly exponential function, since there is no exponential function in Arduino. So we did that procedure by computing real part and imaginary part, then then multiplying. But here we will find the W matrix directly by using exponential function. Here we will get the exponential function output, that is W matrix, and then we are going to directly multiply the matrix and signal. There is no need to write for loop. And then we are going to find the magnitude, that is squared function, same, and absolute of same. This is the procedure to find the magnitude of x of k. This capital X is DFT coefficients. then magnitude of x of k. Then we are going to plot the magnitude spectra. Then we are going to find the maximum of magnitude spectra, dominant frequencies, and then we are going to multiply that index with sampling frequency, and we are going to divide it by length, and then we are going to find the BPM. I'll run the code. This is the two dominant frequencies, and then this is the BPM. We got the BPM as 80. As I said, there is error when we uh, compute the BPM using Arduino, that is Arduino and MATLAB, and there is an error between the procedures, like we computed using DFT and we computed using autocorrelation method, but there is an error of 20 for between the procedures and the softwares. Thank you.